Good afternoon. My name is Pavlo Ardanov. I'm a deputy head at the NGO Permaculture in Ukraine and a research scholar in the University of California, Davis. And we continue the lecture series on designing a plant polyculture. This series is supported by the International Visegrad Fund. And today we continue reviewing algorithms and models for designing polycultures. We will continue with the tool called ROTOR, which means rotation in organic farming system, designed to crop rotation in nitrogen-limited legume-based organic farming system. This tool plans for supplying sufficient fodder, regulation of weed infestation, taking phytosanitary restriction into account, maximizing nitrogen fixation from legumes, and minimizing nitrogen losses via leaching. It takes input data from the field-specific German soil rating index, mainly based on soil type and texture. So if you are using this tool outside of Germany, you need to match your soil type with German rating, as the model is adapted to northeastern Germany. Another input is the mean annual precipitation, and the mean annual precipitation during the winter half of the year, when the risk of nutrient leaching is high. As a basis for generation of crop rotations, algorithm utilizes database of crop-specific annual production activities, which describe the way to produce a specific crop. We will review this later. Database contains 223 crop production activities of 18 crops, each described for 4 different classes of soil. From this database, select activities according to soil quality and type of field management, which might be application of manure, straw harvest, use of forage legume grasses, and catch crops. Catch crop is the fast-growing crop that is grown between successive planting of a main crop to reduce nutrient leaching and transfer of nitrogen to the next main crop. Each crop production activities is characterized by yield according to nitrogen supply from the preceding crop production activities, and also defines the yield of the following activities. The gross margin includes labor cost and cost of machinery, as well as available subsidies from the European Union and from the state of Brandenburg. Rotation scheme is assembled by matching nutrient inputs and outputs of different crop production activities according to farm type, such as cash crop farm with legume grass used as set aside, no manuring, no straw harvest, mixed farm with legume grass forage production, and according to soil quality. It normally starts composing rotation schemes with legume grass as a main crop. You can select desired sequence of crops and duration of rotation cycle, and algorithm will evaluate its performance or suggest optimal production activities for desired crop sequence. Or you can partly define the sequence, and the algorithm will suggest agronomically realistic sequences of crops and production activities. The algorithm also assesses the effect of each crop production activities on weed infestation. The agronomic evaluation is performed based on the overall nitrogen balance, overall weed infestation risks, and economic performance. These values are compared with user-defined threshold values in order to eliminate rotations with a limiting minimum nitrogen supply and maximum weed infestation risk. Maximum frequencies and sequence of crops and crop types within rotation are used as phytosanitary restrictions to control soil-borne pests and diseases. These restrictions can be set off, and limits can be increased by experienced growers to show prospective, potentially more profitable combinations which might be otherwise eliminated. Algorithm selects agronomically sustainable crop rotations according to exclusion criteria, such as a threshold of nitrogen balance with infestation risks, phytosanitary and chronological restrictions. To avoid agronomically unfavorable crop sequences and ineffective use of nitrogen, the following rules are applied. No leaf crop after leaf crop. No wheat after cereals. No grain legumes after grain legumes or legume grass, no manure applications to legumes or legume grass, no preceding crop production activity with low nitrogen residues for crops with high nitrogen demand, such as potato, winter wheat, rape, or silage maize. Model outputs are 3 8-year-long crop rotation ranked according to their economic performance. The algorithm utilizes information from the database of all relevant crops, recorded separately with inputs and outputs, machinery and timing. Different annual crop production activities are included for each crop according to the type of crop preceding and the field operation following, such as ploughing or non-inverting tillage, undersowing crops, using catch crop, manuring, straw harvesting, or mechanical weed control. Crop production activities are evaluated for yield, economic performance, nitrogen balance, nitrate leaching, and weed infestation risks, using data from field experiments, farm trials and surveys, expert knowledge, and soil crop simulation models. All crop production activities are automatically allocated to codes: preceding crop demands and preceding crop supply. These codes are used to determine crop position within a rotation with respect to its preceding and succeeding crops. Each code consists of 2 digits. First defines the type of main crop, and the second, the level of nitrogen residues after harvest of both preceding and following crops. A latter code specifies production activities that establish or take over from undersown catch crop or fodder main crop. Crops are classified into 4 groups. The level of nitrogen residues after harvest is classified as either high or low within each crop group, depending on the type of preceding crop, type of use, which is forage or set aside, and manure application. Amount of nitrogen supply for the following crop is classified into 3 discrete classes: low, medium, or high. The yield of each crop production activity is calculated based on specific crop yield and type of production activity, supply level of nitrogen and manure, precipitation, and soil fertility. The nitrogen balance is quantified using a set of algorithms derived from literature, experimental data, on-farm research, and expert knowledge. It calculates nitrogen removal, fixation, and nitrogen loss through nitrate leaching and ammonium volatilization out of mulched biomass according to site characteristics and preceding crop category. The capability of different catch crops undersown in main crop or stubble seeded to reduce nitrate leaching is also included. The weed infestation risk indices of different weed types, which are perennial, summer annuals, and winter annual, are calculated for every crop production activity by adding the indices of the crop type and different specific cropping measures. The output includes description of proposed crop sequence and recommended production activities for each crop in rotation, yield, nitrogen fixation, leaching removal and nitrogen balance, humus reproduction, weed infestation risks for different groups of weeds depending on soil and farming. You can assess contribution of each crop in rotation as well as performance of rotation cycle in general. And by modifying the inputs, for example, increasing proportion of legumes in mixture to increase nitrogen fixation for the following crops, or addition of catch crop to reduce nitrate leaching, you can optimize desired rotation scheme. In conclusion, one of the primary benefits of ROTOR is the ability to generate and assess complex crop rotation, specifically with overlapping undersown main and cover crops, as it is required for successful organic farming without an external nitrogen supply. In addition, the model reacts sensitively to soil quality and a preceding crop effect with regard to crop yield and nitrate leaching. The next tool for designing crop rotations, which I am going to review, is called ROTAT. It first generates all possible permutations of crops and then selects the feasible crop rotations by applying so-called agronomic filters. It focuses on phytosanitary issues, soil erosion, the use of pesticides, and the long-term dynamic of soil organic matter. First, candidate crops are listed in diminishing orders of marketability and profitability. User can specify main crops, secondary crops, and no preference crops. Secondly, all crops are characterized by their potential role in rotation using expert-based quantitative rating of biological, physical, and chemical characters. You can see these characters in the table above. Finally, the rotation is built up from the first crop on the list by selecting subsequent crops in order to preserve biological soil fertility, minimize soil disturbance, optimize soil coverage, and minimize nitrogen leaching. Results are inspected to ensure that the crop rotation is feasible in terms of harvest time, crop residues, and volunteers from preceding crops. Thus, ROTAT used more trade-based approach, while previously reviewed ROTOR utilized more empirical data based on soil type and farming system. Therefore, ROTAT can reduce the risk of ignoring promising options and can, for example, generate shorter crop rotations with fewer crops, which may be more feasible or desirable for some farmers. The next tool for designing crop rotations, which I'm going to review, is called PRACT, which means prototyping rotation and association with cover crops and no-till. This tool was developed to support the design of appropriate crop sequences for no-till conservation agriculture systems, and a special feature of such system is intercropping with cover crops and production of biomass to serve as a mulch for the next cropping season. Contrary to previously described ROTAT and ROTOR, this tool is able to propose innovative configuration involving newly introduced cover crops, for which data is sparse, and is also able to deal with bigger number of plants and more complex agronomic rules. PRACT was designed for Madagascar, around a database of 28 plants, which are crops, cover crops, or both. Data were collected from expert knowledge developed over more than 12 years of agronomic experiments. The input information for PRACT is composed of Crop and cover crop adaptation to biophysical conditions of different field types or agronomic units. Then agronomic functions of crops and cover crops. Also crop production, including simplicity of management such as sowing, weeding and pest control, and ability to produce during marginal, dry or cold periods. Also association possibilities between crops and cover crops and some pre-crop carryover effects. And finally, agroecological functions of the cropping system described by the same factor as crops. The final output of PRACT is a list of crop and cover crop intercropping in the cropping season and in the off-season over a 3-year period. A further step is to select from among these feasible cropping systems those that fit in within farmers' particular goals, such as desired crop, for example, growing rice every year, or year-round production of cash crop on the most fertile lands, or a cultivation of fodder crops, and constraints, for example, a need for a high production of organic matter. Authors suggest to apply these additional filters at the later stages to increase the chances of identifying innovative cropping systems. Each plant and each cropping system is characterized by a level of production. Agroecological functions include improving soil structure, increasing soil organic matter content and production of biomass, nitrogen fixation and nutrient acquisition from deep soil horizon, weed and pest control, and ease of management. Crops are ranked for each of these parameters. For the focus region in Madagascar, authors defined 17 agronomic units, which are described by the position in the topo sequence, soil fertility and compaction, the drainage or waterlogging status, potential for irrigation management, the possibility or not to support the growth of an off-season cover crop. The possibility of associating plants results mainly from potential competition for light, water, and/or nutrients. Experts excluded all intercropping combinations that are too complicated to manage, which are not interesting from the agronomic perspective, or those that have a low probability of success in a specific agronomic unit. The third step uses more elaborate rules about the crop sequences, which are defined for each agronomic units, but these are generic rules which can be applied to similar location elsewhere based on expert and farmers' knowledge. These rules will ensure a year-round soil coverage, production of sufficient biomass for mulching, accounts for differences between annual and perennial crops, differences in growth rate, in cost of crop establishment and termination, and crop compatibility. PRACT is sufficiently flexible to allow new crops and cover crops to be added, characteristics of the different species to be changed and adjusted, or selection rules to be added, revised or removed. Information on biophysical requirements of local crops can be obtained from literature, databases, current observations and previous experimental results, or extrapolated with certain precaution from similar or related species, or performance of target species in comparable agroeconomical conditions. For this, we can use tools such as Homolog to identify regions with similar conditions. The next tool is used for selecting cover crops for crop rotations. This tool is designed for common commodity crops produced in southeastern USA, such as cotton, corn, peanut, soybean, and wheat. It allows selection of the most efficient cover crop species adapted to the production, rotation, resource concern, and landowner goals. The following goals are available for selection: increasing nitrogen content and reducing leaching, weed and nematode suppression, reducing soil compaction, improving water infiltration, increasing soil organic matter, and providing forage. Another set of input categories describe crop rotation and current production practice, such as current and future cash crop with their planting and harvesting dates, tillage regime, herbicide use, and existing equipment use for planting, managing, and terminating cover crops. Additional inputs are soil pH and drainage. Output is the list of alternative cover crop species from 3 functional groups, which are broadleaves, grasses, and legumes, or it can be less number of groups depending on type of the main crop. Each species is evaluated by the pros and cons for indicated problems, desired benefits, and field conditions, with the information on seed cost and link to detailed crop descriptions. This Excel workbook is open source and may be adapted for specific regions. Now another tool which can be used for calculating average annual income from crop rotations based on provided local data on crop prices, management costs, and number of years in crop rotation. Let's move to the next group of tools. So this one is used for selecting plants when restoring habitat for pollinators. This tool requires 3 data as inputs: a record of local pollinator species and corresponding plants which they visit, an optimality criterion. For example, a planner might want to provide additional floral resources to pollinators of a specific crop outside of the blooming period of this crop. Or alternatively, they can design a plant mix that supports the greatest diversity of native pollinators. And trait information about the plants or pollinators, such as floral bloom period or timing of plant-pollinator interactions. The algorithm subjects an initial population of a plant mixer to several iterations, so-called selection, recombinations, and mutation, keeping track of the best mixtures encountered. So let's review these processes. The population represents the dataset comprising approximately 8,000 wild bees netted on flowers at 16 sites in Northern California Central Valley. Sites were situated in mixed native vegetation, vegetable farms, and orchards. Researchers highlight the limitation of floral visitation metrics, as it can omit rare species, as well as low detectable interaction, for example by nocturnal pollinators. During so-called selection, initial mixtures are created by selecting the first 3 plants species amongst each category of early, middle, or late blooming plants, and adding the next 3 species selected the same manner, and so on. The next 2 operations imitate the process of sexual reproduction, very interesting. So during the recombination, the fraction of previously selected mixtures exchange one component within the group of either early, middle, or late blooming plants, while the rest of the components remains the same. And finally, during the so-called mutation, plants in mixture are sporadically replaced with defined probability, with random plants which are not in the mix. So both recombination and mutation increase the number of plant mixtures, but it can also mutate some good mixtures. An algorithm utilizes 4 separate functions that optimize either pollination visitation or pollination species richness, or floral resource continuity throughout pollinator flying period, or the bloom period of plants. Each function assigns numeric scores to mixtures of plants. Two objective functions are generated by multiplying results of different functions. One that optimizes pollinator visitation, pollinator species richness, and the timing of plant-pollinator interactions. And the second that also optimizes visitation and species richness, but floral bloom period instead of timing of plant-pollinator interactions. Researchers found that 9-species mix selected by either of these functions provides resources to about 98% of native pollinator species. Thus, this tool allows to design floral mixtures to efficiently support vast majority of native pollinators by the small number of plants. Designed mixtures support approximately 20% more pollinators than an expert-driven mix of the same size. Another model which I'm going to review is used for selecting cover crops. And selecting cover crop species means searching for plants with the best trade-off between competition against weeds and competition with the cultivated crops. Cover crop should be able to grow quickly and form soil cover to suppress weeds, and also persist under increasing shade from the canopy of the main crop. SIMBA-CC model have been developed to select the optimal cover crop by predicting long-term growth potential of cover crop based on radiation interception and conversion to biomass. The model runs at a weekly step to reflect growth dynamic. It utilizes plant intrinsic trait parameters and derivate biophysical parameters, such as the change in availability of total and photosynthetically active radiation to the cover crop with radial shading by the main crop. Dynamic of biomass production by the cover crop with age and shading. Length of tissue life with gradual senescence. Leaf area per unit of biomass. Efficiency of light interception by a cover crop. Total leaf area and its change over time. And crop nitrogen demand represented as nitrogen content in the biomass. Model is based on the number of equations, which calculate the interception of photosynthetically active radiation as a function of the radiation, the leaf area index, and the crop-specific interception parameters. Plant maximal productivity as a function of biomass and interception. Dynamic of leaf surface and the proportion of biomass allocated to shoots. Biomass growth and decay. And finally, the nitrogen content in the newly formed biomass. For functional evaluations, researchers defined 3 effect traits based on previously described intrinsic crop traits. The first is mean biomass between 0 and 15 weeks after sowing, which is an indicator of the capacity of the cover crops to compete with weeds. The second is mean biomass between 50 and 150 weeks, which is an indicator of capacity of the cover crops to persist over time. And the third is the sum of nitrogen in the biomass of newly formed plants between 50 and 150 weeks after sowing, which is an indicator of the demand of nitrogen of the cover crop and nutrient competition with the cash crops. For the particular banana cropping system, researchers have been able to calculate minimal biomass to ensure fair control of weeds. Biomass thresholds as an indicator of crop durability under formed canopy. and the rate of mineralization of soil organic matter during the cropping cycle as an indicator of maximum sustainable competition. Finally, I would like to review generalized Lotka-Volterra model, which is famous in ecology, which was employed for designing communities of perennial crops. Authors developed general methodology to predict the yield of different crop mixtures for optimizing, for example, grassland and pasture production. This model seems to be a useful tool for searching optimum crop mixture for overyielding. Overyielding is the situation when polyculture yields more than the highest yielding component species in monoculture. Parameters are extracted from the field experiments involving monocultures and bicultures, combination of two cultures. The biomass was collected and measured at the end of the growing season, when the equilibrium state has been reached. This model would help to design multi-species polycultures based on empirical data on testing yield of monocultures and selected bicultures by combining species from different functional groups, for example, from legumes, cool season grasses, and warm season grasses. And if, for example, presumably we have 5 candidate species in each groups, by combining one species from each group in 3 species combination, we would have 125 possible combinations. If we construct biculture by combining 2 species from 2 different groups, it will be 75 bispecies combinations, which is still a lot. But we can further limit the number of feasible combinations to test, for example, by analyzing seed price or management constraints. It can be potentially used to incorporate empirical information into polyculture design algorithm or software. This model has 4 equilibrium points. Complete extinction, which is always unstable, exclusion of one species, and coexistence of both species. It turned out that the estimated values of the parameters carrying capacity of species and a pairwise interaction coefficient for some species combinations break down conditions of stability for coexistence equilibrium, and thus would imply that the coexistence equilibrium is unstable. In this situation, we still have the freedom to modify the model parameters around the computed means values, provided we keep them within the confidence intervals, in such a way as to transform the unstable equilibrium into a stable one. So in conclusion, which author drew from this study, that most of the polyculture are actually performing as bicultures, and the third and fourth species represent minor contribution to the total yield. There is an optimal number of species that maximize productivity metrics, and as three identified more productive polycultures all involved 3 species. Also, most interactions of random species were negative. Out of 38 measured interspecific interactions, there was 22 negative, 7 null, and 7 positive interactions. Authors concluded that this from experiment draw this conclusion from the experiment with combination of 3, 4, 6, and 7 species belonging to legumes, cool season grasses, and warm season grasses. What might be the possible implication of this model? For example, if the productivity matrix is limited, is not increasing by increasing number of species over 3, we can include more functional groups, as author included in the study, to increase the chances of overyielding. So, for example, we could include long-lived grasses to sustain productivity of mixture in the long term. if functional redundancy does not impact productivity, we can select redundant. We can increase redundancy by selecting species within each group with some additional functionality. So, for example, we can combine early and late season grasses and add drought-tolerant plants within each group. Then we can select multifunctional species to increase the number of ecological services provided without increasing number of species, and thus potentially eliminating the risk of decreasing productivity of polycultures due to competition between multiple species. We can also select and add additional minor species that are not suppressed by dominant species, and in their turn they don't increase the productivity of this dominant species, but these minor species could provide additional services. So, for example, food for pollinators or as anti-helminthic property for cattle. I would like to finish this video lecture by inviting you to subscribe to our Facebook page called Polycultures and Permaculture, where you can follow regular advices from the research literature and from experts on how to design polycultures. And also I would like to invite you to our conference, which is also called Polycultures and Permacultures. It will be organized from 30th of January till 8th of February. It will have several sessions in Warsaw, Poland, in Kiev, Ukraine, in Davis, United States, online sessions, but all sessions will be broadcasted, so you can join either in person or online. And the format of this conference is Research and Practice Conference, so both researchers and farmers are invited. Thank you very much for your attention and good luck.